Let's move past data as an abstract list. To build software that actually scales, you must understand exactly how information locks into the hardware. We are moving past the concept of storing single variables. Today, we're looking at how computer systems engineer and organize massive amounts of data. A common misconception is treating an array like a simple spreadsheet or a visual container, a convenient way to group related items on a screen. But treating data like a conceptual list fails at high volumes. If you toss data into memory wherever it fits, the system has to hunt down scattered fragments, creating massive performance lags. This brings us to the formal, structural representation of a data array used in modern system architecture. To truly understand data at this scale, we have to strip away the aesthetic interfaces and look directly at the raw, linear memory constraints underneath. By strict definition, an array stores multiple values of the exact same data type in contiguous memory locations, meaning zero physical gaps. If a system tries squeezing a new block into a fragmented space, it's rejected, forcing perfect, uninterrupted alignment. When data is stored with gaps, the computer must maintain a map of where every piece lives, burning cycles jumping between addresses, creating massive latency. Arrays function as highly optimized memory maps. Because the data is perfectly aligned, the processor can bypass sequential searching and retrieve any exact value in constant time. Because arrays reflect the physical layout of the hardware, they serve as the mechanical foundation for scalable software engineering. This physical truth begins the exact moment an array is declared. The system immediately reserves a fixed block of specific physical memory addresses for it. We see the math of contiguous storage in these physical addresses. This integer array starts at 1000, the next at 1004, the third at 1008. The computer calculates these gaps using the fixed 4-byte size. It never has to search for the next slot. This means the index is not a human linguistic label. It is a mathematical offset from the base memory address. Target address equals base address plus index multiplied by data size. The first element is right at the base address, so its offset is 0. 1000 plus 0 equals 1000. Subsequent indices land perfectly without scanning. 1000 plus 4 is 1004, plus 8 is 1008. Zero indexing is a mechanical necessity of hardware architecture that enables instantaneous, calculated data retrieval. Because arrays are rigidly bound to these specific physical memory limits, accessing that data requires strict boundary enforcement. If a program attempts to access an unallocated memory offset, like asking for element 5 in a 3-element block, it results in a catastrophic out-of-bounds error. To safely extract data, we traverse the array using a dynamic loop that respects these physical limits. Looking at this Java example, the for loop uses an index variable, I, starting at 0. The loop's condition dynamically matches the exact size of the array, using methods like .length in Java or len in Python, preventing the system from overshooting into unallocated memory. Once an element is securely accessed through this controlled loop, its value can be manipulated exactly like an independent variable. Dynamic loops are the safe engine driving the process, allowing you to traverse the rigid track of the array without crashing into raw system memory. This structural efficiency allows us to replace inefficient patterns. A common mistake is using repetitive, hard-coded if-else structures to count or categorize large datasets. We can see the issue in the left panel of this comparison. This cascaded if-else-if chain forces the computer to evaluate every single condition sequentially. That approach creates significant overhead. Nested decisions demand sequential evaluation. The CPU wastes cycles checking false conditions every single iteration. Contrast that with the array solution on the right. Here, the data value itself acts as the mathematical index. That single line, counts bracket number plus plus, replaces the entire branching logic block. Instead of asking a series of questions, the system performs a direct one-step memory lookup based on the value's index. This enables true scalability. Handling 100 different categories requires zero changes to the control structure. You simply increase the size of the initial array. There is one trade-off. Raw numeric indices lack human context. Remembering that index 5 represents the state of Indiana creates ambiguity for the developer. To solve this, professional developers map named constants to these numeric indices. This maintains readability for humans without sacrificing execution speed for the machine. Utilizing arrays converts data categorization from a sequential bottleneck into a scalable, constant-time operation. Arrays act as the crucial architectural bridge connecting the physical memory of the hardware to high-level software logic. Aligning data of the same type into neighboring physical slots is the reason rapid mathematical indexing is possible. This underlying mechanical truth is absolute, regardless of whether you are writing scripts in Python, C++, or Java. Understanding this physical layer allows you to write leaner, more efficient code than a programmer who only memorizes syntax. While programming languages evolve, the physical laws of data structures remain constant. Effective engineering requires seeing past the syntax of the script to the physical resources it consumes. Mastering these structures allows a developer to manage memory constraints that would otherwise crash a system under heavy load. To build systems capable of scaling infinitely, you must first understand how to strictly define their boundaries in physical memory.